Okay, let's get started. I guess there are a few attendees this morning, but it's a fairly critical and important lesson because the whole framework of modifying or developing the ability to modify our training loop, we have all the basics that we've built up to this point are kind of put together in this lesson in order to build the learner class and really understand how that the learner class from Mini AI helps us build and experiment very quickly with a lot of different configurations and neural networks. So let's get going. I'll share my screen and let me know when you can see it.
We can see it.
Okay, thanks. FYI, if you try to run this notebook, at least I encountered some difficulties. I had to add a few things. Maybe I was playing around with it too much and modified some things, but if you do ping me on Slack, and I might be able to help you get around some problems I saw. But anyways, moving along, we kind of import some of the required libraries and tools, and I had to add this neat training import. I don't know whether that was needed. But anyway, some configuration stuff, and then we do the same thing that we have done so far and load the load the Passion MNIST data set from Hugging Face, do the in-place transforms, which we already seen in a prior notebook. We select a large batch size, 1024, and apply the transform, so we get a transform data set. And this was something else that should have worked automatically, but didn't. I had to import, re-import certain utilities and add this data loaders class. By the way, if you're not familiar, I think I put in the Slack channel the various decorators that so far we've seen. One of them is the add class method decorator, which is typically used as an alternative to the init function in a sense. So init typically sets up your class, but if you want an alternate method for constructing the class, then you can put a class method to a method or a class method decorator, and that will help us build data loaders using a slightly different construction. So that's typically what a class method decorator is used for. And so we build a class method so we can say data loaders from DD and provide a data set and a batch size and say as tuple is true, and we'll get collated data sets because we use the collate function and provide the data set as input. So we apply that function to our Passion MNIST data set, and that enables us to then get the training data loaders from which we can get XB and YB. And that's XB, 1024 by 784 image, 10,024 images, each of 784, and these are obviously binary values, and then YB of 10, these are the labels, or these are the indices to our label function, as we've seen many times before. So now we'll just look, and I kind of briefly touched on this last class as well, but because we'll be focusing on this function so much and building it up in complexity, and actually if you listen to the lectures, you'll see that he builds multiple versions of it and then finally settles on a decorated version of this, which allows us to use all the callbacks that that will allow us to get the maximum flexibility in our training loop. So what we're trying to do, just to get an overall idea, is to replace the fit function with something of a customizable training loop so that almost every line of the code of our training loop is tunable based on our callback. So what we don't want to do is continue to change the fit function each time we have to deal with a new model or a slightly different configuration of the model, like multiple inputs and so on and so forth. So we let the fit function equivalent, which is the learner, remains the same, and then we just modify the callbacks as we'll see. So that's kind of the goal overall of building the learner framework or the learner class. And as we'll see in lessons down the road, this building a learner class, allowing for customization, will really help us experiment very quickly with a variety of capabilities that we can then build into our models. So let's look at what the learner class looks like. The first learner we build is a very inflexible one, but it gives us the basic framework. So what is the basic framework? Well, when you call a learner, we provide it. So a learner has a specific model. It has data loaders. Both training and validation can be provided. It has a loss function. We give it a learning rate, and we also specify an optimization function. The default optimization we use is the optim.std. Okay, and this is, as we've seen before, just the fast port store attributes, so you don't have to do self.model, and so on and so forth. The way this learner function works is it first calls fit. Now, the reason this is inflexible learner is because we are hard coding this learner for a particular type of usage, and the particular usage that we'll be focusing on is something that allows us to predict the accuracy of a multi-class, such as the fashion MNIST. So in fashion MNIST, we want to say, what's the, out of 10 classes, what class does this image belong to? So we're going to customize the learner initially or fix it to do just that task. And then as we progress, we'll allow it to become much more general. So first, learner, when the learner runs, then what happens is the fit function is called. It creates a few lists. It moves the model to the device. Then it calls the optimizer and takes the model's parameters, which are, the model is already here. So because we have been provided the model, it accesses the model's parameters, and whatever learning rate has been provided to it as an input, it kind of takes the learning rate. Now, the only parameter to be provided to the fit function itself is the number of epochs that you want to fit. Everything else is provided when you build it, is pre-provided to the learner class, as you can see in the init function. So a learner class is for a specific model, data loaders, loss function, optimization function. And then you say, how many epochs do you want to train this learner for? And once, then it, as I said, it takes in an optimizer, defines the number of epochs which have been provided. And then for each epoch, in the range of number of epochs, here's what it does. It calls the one epoch function with a parameter passed in as true. And that is the training parameter. And so self.oneEpoch is called. So let's go look at what one epoch does. One epoch just says, and the parameter passed in is train. This is true if it's in the train. If we want the neural network to be in the training mode, so it sets the training mode, model's training mode to train, which is true, because we have passed in true here. Then the data loaders, we pick the data loader we want. Because its train is true now, we pick the training data loader, and then we enumerate the training data loader, get the first batch and the actual contents of the batch, and then we call self.oneBatch. So now let's look at what, so remember, we started with fit, called one epoch with training of true, came to one epoch, now we are calling one batch within an epoch. So we go to one batch and move the data. So the model is moved to the GPU right here as soon as we call fit. The data is moved here in one batch. We move to device the batch data, extract X and Y, run the model, get the predictions, calculate the loss. And if the model is in training, then we backpropagate, use the optimizer to step, do the zero grad. We have seen all this and coded it ourselves. And then this is the first three lines are executed if you're in training mode. And this line is executed in any case, which is with .nograd, you calculate the stats. And the calculate stats function is something which, again, this is hard-coded, but it calculates the accuracy. So it says, oh, I take the predictions argmax along dimension 1, compare it to the labels, convert it to floats, sum it up, and then I append that. I check how many in my batch. I add the losses, and then to the count of n, which is stored in the list ends, I just append the value from this batch. Okay, and then once I'm done, I've finished with self.one batch. Then n is sum of self.n, so it kind of adds up all the batch numbers so far, and then it prints this value, the epoch, whether training is true or false, the average of the losses, and the sum of the accuracy, right? Average. And then once this is done, it goes back here, and it says with dot.nograd self.one epoch false. So it goes back, and now training is false. So it loads the validation data loader, does the self.one batch, goes to the batch, and then the self.calc stats will only be done during the validation, not during no, actually self.calc stats is done for sure in validation, but also once training is completed. So that's the nature of the first learner class that we build. It's inflexible because it's only coded to do the accuracy, kind of calculate the average of the losses, and accuracy for a multi-class classification problem. Okay. Any questions on this first framework of the learner that we built? So we can then very quickly try it out on the model, and it will tell us, it will print out the values it's fitting for just one epoch, and even the single epoch, as you can see, will have a learner, will have a training epoch and a validation epoch. So that's what this is, and you can see that the values correspond. These two values are the losses, and these two values are our accuracy. So a training accuracy and a validation accuracy. And the training flag, which is true in the first case and false in the next case. Now, the epoch number doesn't change because training and validation, we execute both as part of the same epoch. Any questions? Okay, now the next steps we take is what makes the whole learner framework incredibly flexible. We define some exceptions. Again, in this particular lesson and the next lesson, one of the things that will become important is to kind of be very familiar with the Python concepts of decorators, configuration managers, the try except way of handling certain control of execution loop, things of that nature. So if you're not familiar, I'll post some also properties and what they mean. So familiarize yourself with those constructs, because without understanding of those constructs, it becomes very hard to understand what is exactly going on, and go back and retouch upon the callback concepts as well. So we define a callback class. The only thing we put in it in the base class is an order. The thing to remember about order, if there's one thing you take away from order, all callbacks have an order. And you will see shortly that we'll sort the callbacks in the order that we want to execute. Higher order is lower priority, and the 0 is the highest priority. So the lowest priority, meaning 0, will be executed first. Anything higher than 0 will be executed subsequently. So if you have 0, 5, and 10, 0 priority callbacks will get executed first, 5 next, 10 last. Then we define this run callback method. I'll just briefly mention what they do, but the understanding of its usage is much better explained when we see the code for the improved learner. But just quickly, run callbacks takes a bunch of callbacks, takes the name of a method, it takes in a learner as an input, and then for every callback in a set of callbacks or a list of callbacks, using the order key, sort it. So this is what helps the callbacks to be ordered in some sequence or in some priority order, so that the callbacks can be executed according to the order that is specified in the order. And then what do? You get the attribute, which is the name of the method. If it's not specified, use none. And if we have a method, which we would, if it's called run callbacks and provided it a method name, then if the method is not none, then call that method on the learner. Okay, so that's what that does. A completion callback. This is an example of what we will code in order to kind of utilize, and this is where we begin to utilize the callback functions that we have so far played with in toy environments. And even this very first example is more of a simple example to illustrate the use of callback. So let's inherit from the callback base class with just as an order. And we say before fit, I'm going to define a before fit method, after batch method, and an after fit method. What does the before fit method do? It just sets a callback value self.count. So this completion callback will have a count value of 0 before it begins to fit. After batch, after one batch of data has been processed, I want the count to increment. And after I've finished running my fit function completely, which is after fit, then I want to print out how many batches has my fit function processed so far. So that is the simple example of a callback that we can code. And we can manually run it. We just put the callbacks in a list and we instantiate the completion callback that we just coded. So these methods are coded in the completion callback. So if we now run the CBS, if we now execute this function, run CBS, and call CBS, which is an instance of completion callback, then what will happen? We'll come here and say for callback in sorted, and now there's only one callback. So there's nothing, in a sense, nothing to sort. It's just this callback, the completion callback. It'll say before fit, so it will set count to 0. After batch, then we are running after batch next, so it will increment the count to 1, and then run callback after fit. So it will go here and execute this, and it ought to say that the result is 1. So it should say completed, and our count would be 1 batches. So let's see whether that's what happens. Right? So he just says, okay, we have done it manually, and the point he's making in the next several cells is to say, try and kind of, even as you code this callback or many things that are coded in the lesson, play with them, and if there are pieces of code that you don't get, separate it out, split it into single lines, and then execute them to make sure that you understand what is happening. So CB is CBS 0. He just shows what is in the CBS. It's a list. It's a completion callback. If you just get the attributes, and we have to, this is where I had to modify, because the notebook, you have to pass in a learner to the way that the get attribute is coded. Earlier, you didn't have to. So as we progressed in the class, we made changes to the code. And if we look at the callback count after we have executed after batch and before fit. So before fit, it initializes count. After batch, it increments it. So now it's already incremented. So when you execute cb.count, it will be 1. And when we get the attribute after fit and pass in the learner, it will print. And that's exactly what we see here, right? So the next step we are going to do is improve the learner, but only from the standpoint, so he drops some functionality like calculate stats and stuff in order to focus on what we are trying to do in the learner when we bring in the concept of callbacks. Okay, so this is the next step in kind of complexifying or adding complexity to the learner by bringing in the concept of callbacks and how they integrate with the learner to provide enhanced capability. This is not the final learner class. We'll go through 2 more steps before we get to the final learner class that we will be using in the rest of the course. So let's again look at the framework. It's very similar as we saw to the previous setup. We have fit, we have 1 epoch, and we have 1 batch. We are familiar with this setup by now. So but there are a few other functions like callback added here. So let's look at what happens in this case. Again, we provide the same things as we saw before, store them off, Then we come to fit, and in fit, we again provided the number of epochs. These things are already familiar to you. Now let's begin to look at how we use the callbacks. So we put the callbacks in a try except loop so that if we, earlier we had defined the cancel fit exception. So we try, provided we do not see a cancel fit exception, we execute this code. If on the other hand, we see a cancel fit exception, we don't even fit. We just raise the exception and get out of the loop. So same thing happens in multiple situations. So this is something that he does, is to utilize the try except construct as a control flow structure to control the execution or escape from execution. So assuming we have the before fit callback defined, right? Then what we do is we try self.callback before fit. Certain things therefore will be done. We should, or looking at it other way, we should in this callback specify anything we want done before we begin the fit or before we begin the fitting process. So anything we want to customize before we begin fitting will be specified in the callback before fit. Now, then we enter and execute the same code as we used to do before. For epochs, the training thing is on, so we execute the self.one epoch and pass in true. So we go to one epoch. One epoch training is true, the train flag is true, so set the model in the training mode, load the training data loaders, again get into a try except loop. The try except loop in this case, the except is a cancel epoch exception. So we are in fit and we are now in the process of executing an epoch, but we may not want to execute the epoch at all when we cancel the epoch. Assuming we don't cancel it, then we call the callback before epoch. So anything in the before epoch callback should typically be code that does anything to our data or model before we want to execute an epoch. There may be some things that we would like to do, and that's the code which will go in the callback before epoch. Then the rest of the code should be very similar for self.iter and self.batch in the enumerated data loader. So we'll just get the iteration number and the batch values. But again, we are now going to execute the batch, right? So before that, we again have a try except loop. In this case, the exception will be the cancel batch exception, right? And so we then if that isn't raised, we execute before batch. So think about the flexibility that we've got. We could do certain things before we fit, provided there's no cancel fit exception. Then we get into an epoch. We can do certain things before the epoch in the before epoch callback. Then we get into a batch. In the before batch callback, we could do things that we want to do before the batch is executed. Then we call self.one batch. So we go here, call it, do the predictions, do the loss. If it is training, we do all this stuff, right? If there's not training, we don't do any of these. We just return, and after executing self.one batch, what do? We call after batch. So again, on the way in, we have three callback opportunities. One, at least as of now, in this learner. One is before fit, before epoch, before batch. As we exit, you'll see the exact equivalence, right? After batch, after epoch, after fit. So you'll see after batch, and then once the batch is done, and we haven't had any exceptions, self.callback after epoch, and once the whole, all this for this part, when the training is on, then we'll go to self.one epoch false to go through this one epoch loop and the one batch loop, but with the training set to false, right? And then when all that is done, we come back here and say, is there anything else that is specified in the callback that we may need to do after we have done fitting, right? And in any time this self.callback is executed, what does that do? Now that's what is defined here. So whenever a self.callback, and we say before fit, before batch, after batch, whatever. So that's the method name. And what that does is it executes the callbacks, right? So run callback, it runs callbacks, and we have just seen what run callbacks is, right? It just sorts the callbacks in the order and then executes each of them. We've just seen that. Yeah, it sorts the callbacks in our callbacks, and depending on the method, gets the method, and it calls the method, passes in a learner object. So that is what the callback, self.callback before fit. So that means the method name is before fit. It will run the callbacks. It will call the particular callback. Run the callback. It's the self.callback, which will be a list. From that, it will pick the method name, and self is the learner object that's passed into it. Any questions of what is going on with this learner, where we have begun to utilize the ability to customize the entire function?
No, I think it's clear, but I just had a question. Why is it called callback? It looks like it's just a method. It could be any name, right? It doesn't have
yeah, but it is
specific properties.
The concept.
Yeah.
Yeah, the concept that he's using is that of a callback that we went into, I think, in the prior lesson with many examples, right? That you register things that you want to do with the function. So it's very much like the concept of callback. So yeah, you could call it anything you want, but it looks and executes very much like a callback. You register the callbacks with these various names, and then when you hit that particular point in the code, you execute a set of functions that you want the program to be able to do, and that kind of structure in code is typically called a callback. So he just refers to it as callback.
Oh, okay. I think I missed that session. Was it 2 weeks ago that you
might be 2 or last week? I don't recall quite which one it was. Yeah.
Okay, I'll look at
a lot of details. Yeah.
Okay.
We went into a lot of details of how callbacks work with very simple examples.
Oh, okay, great. I'll take a look. I think, yeah, I was here last week, but the week before I wasn't. Thanks.
Yeah, I think it was that week. Any other questions? Okay, so now we have this learner, which is now beginning to use our callbacks, right? And we provide it a model. We take the same data, and the learner that we are using is provided with the model, the data loaders. We are defining the cross entropy. We are using a sequential model that's just 2 linear layers with a ReLU in between. We're providing a learning rate of 0.2. And notice here, we are providing the completion callback in our callbacks, right? So we begin to utilize callbacks. So the completion callback, remember what it did? It simply added these 3 lines: before fit, after batch, after fit, right? So now, if the completion callback is provided to our turning to our learner, you should be able to predict in a way what will be the result, right? When it executes before fit, it will initialize the count. After it executes a batch, it will increment the count. And once the fit is done, it will print completed batches, right? Now, if you want to be precise, there is a little bit of a kind of count issue here, because we execute kind of, the way he has it set up here is that we execute the training and then again go and execute the validation. So it will say 2 batches, even though technically we execute, typically in deep learning, we kind of call a batch both a training and a validation loop. In this case, it counts as 2 batches. But that's a net. The point is to understand how callbacks work. So, so now when we provide the completion callback to our learner and fit with 1 cycle, it will execute. Unfortunately, I got the slower version, not the best GPU. So while it executes, we'll keep going, but eventually it will execute and tell us how many batches it's completed. Okay. Now let's code a slightly different callback. And in this callback, he just wants to illustrate how we can execute, for example, using the concept of callback, how we can just make our learner just execute a single batch, and then using our exception, stop executing, right? So the interesting thing, and these are the kinds of things I'd encourage you to play with. I'm not going to do it here in the interest of time, but there is a reason he makes the order of the single batch callback 1. Now, the important thing to notice is the order in which you list it, the order in which you build the callbacks list is unimportant, because remember that the order when the run CDS or self-serve callback is called, and that calls run CDS, callbacks are sorted based on their internal order. So the order in which you specify this is completely irrelevant because it will sort itself. Now, if you see in the video, he first forgets to code the order of this as being lower, I should say, executing after the completion callback executes. Instead, he reads both of them as order 0. When that happens, then it turns out that the single batch callback executes even before the completion callback does, so you don't see anything printed out. Therefore, he realizes that that's a mistake, and he kind of deprioritizes the single batch callback. By deprioritizes, I mean first you run the completion callback. Remember, lower value of order is higher priority. So order 0 is what completion callback is, and then single batch callback is order 1. So here, even though you are specifying it in this sequence, it's the completion callback that it gets executed first, then the single batch callback. And the single batch callback has nothing but says, after a batch is done, raise the cancel epoch exception. And by the way, also in his code, I think he has cancel bit exception. I think this thing, if it's better, it sees if you code it as a cancel epoch exception. So this is just another example of how you can code very simple things and control what happens. So see here, what has happened is it just runs a single batch, and even though it runs a single batch, the reason it says completed 2 batches is because of the problem that I mentioned, right? He just increments count for a batch, and the way at least currently the learner is set up, a batch means it runs a training loop and a validation batch and a training batch, and for each of that it calculates it as a batch. So that's why it says 2 batches. Technically speaking, that's a batch, but it doesn't matter. It's as long as you understand what's happening. Now, these are very simple examples. Let's get into, and the goal, as we said, is to build a flexible learner, right? So far, what we have done is we have hard-coded the accuracy. We have hard-coded kind of some of the functionality that we would be using the learner for. For example, at least right now, we can only use it for multi-class accuracy. What if we wanted to build a learner and a framework that does a variety of things, which is obviously our goal, right? Not just have a framework that works for multi-class accuracy solver. So the way to accomplish that is to build a metrics class, and we're going to subclass the metrics class in order to build different types of metrics. So what are those? Let's start with rebuilding what we already want or have, which is a multi-class accuracy. So we define a metric class. It has certain methods. The first is reset. So before we calculate any metrics, we reset it. And what we reset the values and the ends. The ends are typically the number of things that we want to calculate the metrics for. Then there is an add method in metric, which just says here, and to it we pass in the inputs, the targets or the labels, and then n equals 1 just says the default number of inputs we give to the add is a single value, right? And then the self last says calculate, and self.calc, and we'll define what calc does depending on what we want to do, right? So this base metric class just defines self.calc and passing the input and the target. Now, typically, what we'll do when we subclass metric is define what our calculation needs to be. So if we want our accuracy, if we want the metric to be accuracy, then you define an accuracy subclass, inherit from the metric class, and override the calc method of the base metric class to be, and remember the base metric class has inputs and targets for the calc method. Take that, return inputs equals targets float sum, which is basically the calculation for accuracy. If on the other hand, you wanted to calculate some other value, then you could change the calc method here to do whatever you wanted it to do. Now, this is the place where you also, to finish up the code, you append the last value into the vals, and you append the n, which is the number of items, into the count of items, and then you define a property value. Typically, I'll just summarize property, but again, I believe I've provided links, but if not, I'll provide in Slack some links to what property decorator in Python does. In this case, it simply converts the method so that you can access it as an attribute. So you can do, for example, an instance of metric dot value and not have the brackets or parentheses around value. So the value just says that, you know, you take the number count of n, which is n's, and then you multiply the n's times the values, sum it up, and do the average. So this basically is the average. So what you will find is, because the metric anyway calculates a value, which is the average, you can use the base metric itself to calculate your loss. So you set it up so for loss, you can just use the base class of metric. For accuracy, you need to override the calc. Any questions on this code or what it does? Okay, so moving along, it just gives you an example of how you calculate accuracy. So add is an instance of accuracy, and then using the accuracy.add, you add this tensor as input, this tensor as output, so you can see and compare what happens to the value and why you get the value you do here, because it'll be 0.5 since you know, you can match what inputs and targets are matching, and again add another value, and then it says that these two are averaged out because it's 0.5 plus 0.4, and there are two tensors we have provided so far. So you add the 2, 0.9 by 2 will be 0.45. Okay, and as I mentioned, if you just want to calculate the average, that's done by the base metric itself. So you just define loss as a metric, loss.add 0.6 with an n of 32. So let's say we have 32 examples in our first batch, and it gives us a loss of 0.6, and 2 examples in our second batch giving us a loss of 0.9. Then the loss value will just be the rounded weighted average. So it will be 32.9.6 plus 2 times 0.9 and divided by the 34 values we have provided. And this is the round to 2 digits. And it just says, hey, is my expected value the same as loss value? Any question again? Not, I'm going to keep going. The next callback that we define, and we'll typically be using this callback quite a bit, is to move some of our stuff onto the device that we want, right? And then what we do with the device callback is, before we fit, if the model in our learner has an attribute 2, then move the model to self.device, and self.device will be our default device. And we have seen before, he has this line of code where, depending on whether you're executing on a Mac, executing on a GPU, or you know, something else, you move it accordingly to the device, whether you have CUDA, or if you don't have both, then it's on the CPU. And then the before batch just says learn.batch to device, move the batch to the device. So this moves the model, this moves the data, right? So that's what our device callback is going to do. And again, here he has not played around with the order. So that means our order is 0. So it executes at high priority. So now make sure that the device callback works with the learner, right? You coded it, let's check it out. And we run it. We just provide the device callback and the completion callback. So remember here, it doesn't really matter in which order it executes, but it basically moves the device, moves the values to the device callback, and then executes the completion callback. So we have successfully integrated, if you will, or executed an example of the learner with a device callback and with completion callback, 2 callbacks, right? What he then moves on to show us is he coded the metric class himself, but there is multi-class accuracy that's available in Torch eval of PyTorch. So you can kind of begin to use that now that we understand what a metric class is and how to modify it and stuff. We can now use similar concepts from PyTorch. So multi-class accuracy metric, we use that multi-class accuracy, and we also import mean. Those methods from Torch eval are slightly different because they have not add but update. So that means metric.update these 2 tensors, and then also not whatever we had coded it, but it uses compute. So that tells us that we get the value out. Computing accuracy after a reset without data is meaningless, right? So you just reset the data and then you compute. It will obviously give you an AND because you just reset the data. There's nothing in the metrics to compute, so it returns a NaN value. Now, one of the things he points out is for some reason the PyTorch eval metrics doesn't execute very well or doesn't work very well with tensors that continue to exist on the GPU, on the graphics processor, which is where we execute most of our training loop. So in order to execute any of the metric stuff, we need to move the data onto the CPU before, or at least that was his observation. So he has this thing where he defines a 2 CPU function, where depending on whether it's a mapping, a list, or a tuple, all we do is move the appropriate thing onto the CPU, right? And whenever we do a tensor and we move it to a CPU, more often than not, you want to detach. And what the detach thing does is, remember that in a tensor, any tensor typically has, we are using tensors and in training and stuff, it has this whole sequence of gradients that are attached to the tensor as well, as it has gone through evaluation in the training loop. The detach method on any tensor says, forget about all the gradients, just take the value of the tensor. You don't worry about all the gradients of it, and then just move that tensor onto the CPU, because we're only interested in the tensor. We're only interested in the actual value, not all the gradients that go with the tensor. And then we return it as float if it's float 16, otherwise just return it as it is. So this 2 CPU function is something that he says is very useful, at least without it, things get gnarly if you use Torch eval. So now we redefine the metrics callback using Torch eval's metric. And again, much like the learner loop, we use or kind of code it in such a way that we can customize the metrics in a lot of ways. Okay, so how does he do that? This is just processing the various names of the metrics that you can pass as positional values or as keyword arguments. He just combines them, sticks them all into self.metrics, and creates a copy of all the metrics that you want to track. And again, as we've seen, even in the case of our example, but he just repeats it here, all metrics, but the metric loss is basically the mean. It's just the weighted average of the loss, right? And then what we do is define the various steps that we want to take. Before fit, what do we want to do? Before fit, we say that before you start fitting, the learner's metric class is self. What does this self mean? It's an instance of the metrics callback. So we tell the learner that we, meaning this metrics callback, are the learner's metrics callback. So that's what this single line of code does. Then before we execute an epoch, we just reset all the values of our metrics. Then after epoch is executed, right, for every metric, we, in the metrics dictionary, we kind of put the values by taking the computed values. So this is where we call the computation of the metrics class and sticking the value depending on the name of the metric. And there are two other logs thing that we want. Log of epoch is basically the epoch we are in, which is the learner's epoch value. And the log of train is the flag value of train if the model is in the training mode, otherwise it's eval, right? And then we call self._log and pass in the log dictionary. So log is now a dictionary, and the values of log are the various metrics that we want to compute, and two other metrics that we had, epoch and the train. The reason he's coded it as self._log and then call the log is because now you can independently code _log to be whatever the dictionary you're passing it, and you can just say print. But you could potentially in the future modify this, send your stuff if you want to weights and biases, which is a whole infrastructure used to track a variety of plots that you want to track. So the reason to separately call another method and pass in our dictionary is to allow that flexibility. He could otherwise have just done simply what he did here. If all you're doing is printing, you could just add a line of code here saying print and you'll be done. But this call and setup is so that you can modify it and make it more complex in the future. And then after each batch is done, we grab the input and the target, put on that CPU, and for every metric value, you update and you move the predictions to the CPU and also the target, and then you update the loss. Okay. And you want to provide it the weight because you obviously want to weigh the losses according to the formula of, depending on the values in each batch, you would want to calculate the average loss over all batches. Any questions on coding of this metrics callback class? Okay, and now we just call the model, instantiates the metrics callback with an accuracy of multi-class accuracy. And then the two callbacks we are passing are the device callback, which means we need to move it on. There is no completion callback called here, and then the metrics. So because we call the metrics that we have defined so far, we have seen are accuracy, loss, epoch, and train. Right now comes the kind of the penultimate learner that we're going to build. In this case, I'll not go through all of the code, primarily because what happens in the class is he uses a context manager to build the flexible learner, completes building it, uses it in the subsequent class or through the next week or two, figures out that there is a problem with the usage of the context manager. There are certain exceptions that don't execute within a context manager in the way he expects them to. And therefore, he switches back to using a decorator method of using callbacks. So I'll spend more time on the decorator method because that is eventually what we're going to be using as the learner finally. But I'll just explain a couple of key points from this learner, not so much the context manager details as much as just a couple of points which carry over to the decorator-based learner as well. So let's get going with that. With the learner, now there are the same things that are being passed in as before. He uses to store the callbacks which are passed into the learner, he uses the L, which is kind of a list, but it's the fast core list. And a couple of things that the fast core list does, you should go and look at the fast core library. I provided the links already. I'll again provide direct link to the L. I also have it in the notebook, but I'll provide these links. But you should look at what L does compared to a traditional Python list. One of the key things I remember is that, and I can't quite recall or explain why he uses an L here instead of just a Python list. But one of the key things about the L that I recall from prior work with it is that it's an L elements of L can index into an L, which you can't do with a list. Now, I don't know whether he's really using that here or not, but anyway, think of it practical terms as a list because it has all the capabilities of a list. Store the callback there and then stores all the attributes. Again, we'll be using the context manager in some other context as we move forward, so familiarize yourself with that. But in this case, what it tries to do is use the context manager to execute the before fit and after fit and the various callbacks. And he uses the name passed to the context manager as the context in which you execute code. Again, as I said, he skips from using context manager to using decorators. So forget about that aspect for now. The important thing here is to notice the change in the training loop that, assuming we have done all the callbacks, structured the callbacks similarly. That is, we have a before fit, we have a before epoch, and we have a before batch. Then when we are done, and while getting out, we also have after batch, after epoch, and an after fit, right? Those are the 6 callbacks that we control. In addition, the key difference that he does, and this gives you even more fine-tuned ability to tune almost every line of code in your training loop, is instead of calling and within the one epoch, within when we begin to execute the batch, right? So you can see, compared to the prior learner, there is still the fit. There are some additional functions that there's still the callback. There's a get atra and a property of training, which we'll come to in a minute. But one key thing which is missing is the one batch. That's because the one batch kind of is swallowed up here. And within the context of the batch, there's some difference to how we execute the lines of code that we were executing previously, if you go back and compare, in the self.one batch call. And what we do here is we just say, we call self, and self is the learner. So we call predict method of the learner. We call get loss. And if we are in the training loop, we call backward, step, and zero grad. So we have called now these 5, actually not self.training. Self.training is something that's passed in, but predict, get loss, backward, step, and zero grad. Now keep this in mind as compared to what the call used to look like in the one batch code, right? It used to look like self.pred, self.model, and callback. Instead, we're just doing self.predict as a method, then we're just doing self.loss as a method, then we're just doing self.backward, not self.loss.backward, just self.backward, self.step, self.zero grad. Now, how do we do those things in this kind of manner is what is relevant here. So when it comes to this portion of the code within the one epoch, and we say self.predict, there is no predict attribute or method in the learner class. We haven't defined it. So what happens when an attribute in Python that's not defined for a class is accessed? Well, it will exist, and this is why some of the Python details are important. It goes and executes the get atra with the name of the method. So if you say self.predict, predict is not there in the particular instance, goes look for it in the class, not there either. So it will execute get atra. What do we do when we have these 5 things: predict, get loss, backward, step, and zero grad? If the name is in one of these 5 methods, then we return a partial of the callback with the particular name. So what we are saying is, if we come to this portion of the code, and if we hit any one of these 5, then I want you to execute what is in a callback with the name, with one of these 5 names. So now we have not only done the before fit, after fit, before epoch, after epoch, before batch, after batch callbacks, we have also instituted 5 other callbacks: predict, get lost, backwards, step, and zero grad, which we can customize to our need. And that is supported by the learner infrastructure right now. And if none of these exist, then obviously raise the attribute error with the name if it's not these 5. So you can't do any arbitrary thing, but if it is these 5, then it will call the callback. And the callback function is the same as before. The property for the training is essentially just saying that a training is whether the model is in the training mode or in the evaluation mode. That's all that property of training does, right? So that's the relevant part of this code that we need to understand, right? And run callbacks still does the same thing as before. So now that we have said we want the callbacks with these 5 things, then we obviously need to code the callback that does execute those 5 methods, right? So we code that in something called a training callback, which has, and this is where, for example, it's important to kind of watch the classes in video and watch it in sequence. And sometimes because he's teaching it live and and also building the mini AI and the learner framework and things on the fly as he does the course and the classes, then he kind of makes changes in subsequent lessons and goes back and modifies the prior lessons notebook. So the point, here's an example of that. Earlier, if you look at the code in the class video, there wasn't a number of inputs, but he adds that in, I think, lesson 17 or 18 and provides a number of inputs. Why? Because as we'll see when we start doing diffusion models and stuff, we may want to provide more than one input. So far, we have never had that challenge, right? We always just provided a single picture. But what if we wanted to provide multiple pictures? What if, for example, we wanted to say, transfer the style from one image to another image? Well, we have 2 images we are providing as input. So how do we obviously don't want to rebuild the learner completely from the ground up just because we have 2 inputs. So this provides the flexibility to do that. We specify the number of inputs, store it away. And then we define the 5 things that we wanted to define. So what do we do in predict? We just say the predicts of learn is learn.model star learn.batch, which will mean this will unpack the number of inputs. So it will pass up to the number of inputs to our model. And then when we want to calculate the loss, we exclude the inputs. So that's why it's self.input : so we forget about this. An input could be 2 inputs or 1 input. We exclude that, take all the rest of the value, and we use that for the loss. The rest of it is pretty straightforward. Any questions on what I've explained? I don't need it or not. Okay. He codes yet another callback, calls the progress callback. I'm again not, interest of time, I'm not going to go through the details of this. You can study it yourself, the bottom line of what he does here is he begins to utilize a progress bar class, which one of his co-workers initially in Fast AI, person who is now at second phase, Sylvain Guder, who wrote the book with him as well. He co-wrote the book with Jeremy about deep learning. He coded this thing where you can have progress of your training indicated. So there is a master bar that kind of encapsulates the number of epochs. So it provides you the bar chart. It says how many epochs are running, puts that on top of that, and you kind of begin to have fancy charts and plots to indicate how well your training is progressing. And that's what the progress callback is for. And you can see what he does here, right? And this is another interesting way to ensure that the callbacks are executed in the desired order that you want. He makes the progress callback one order more than the order of the metrics callback. So what will this ensure? Can somebody tell me, so when will this callback execute relative to the metrics callback, before or after?
It will execute after the metrics callback.
Yeah. And because, as I said, lower order is high priority, so the metrics order callback will execute, then the progress callback. And the reason for it is you want the metrics to be calculated so that you can display them in the metrics callback. So that you can display them in the progress callback. So that's kind of something to keep in mind, that if you wanted to ensure order, and you want to ensure that something relative to something else, then you can just specify it this way, that just put an order after the callback, and that will ensure what happens is, you save the rest of it is fairly kind of self-explanatory code. Plot before you fit, there is a number of epoch, but what you do is you enclose the number of epochs in a master bar. So you'll see the green bar when we start executing. And if the learner has the attributes such as metrics, it has the metrics attribute, then take the log as the progress callbacks log. Remember that we put the metrics in the log, the dictionary, right? And then we say store the losses or initiate the loss in validation. The log just says our logs. The log now writes to the progress bar. Remember that the log earlier just said print B. In this case, we can now write to the progress bar. So the values are written in the progress bar as the progression happens. Before we, before epoch, then the wrap progress bar around the epoch, set some comments, and then after the plot append losses, and after the epoch, in fact, this is another example of something that he coded after the class was over. He codes a validation loss that can be printed as well. So the progress callback, again, I'd encourage you offline to play with every one of these callbacks and add or delete things so that you understand how they work. But now we provide a progress callback, a train callback, and a device callback, as well as the metrics callback. So now we've started to really customize. So we are providing 4 callbacks. Device callback puts things on the device. Remember, training callback is what modifies those 5 things: predict, loss, backward, step, and all that. The metrics is the desired metrics. The progress callback sticks those metrics onto the progress. The rest of it is the same, and now we are fitting for 2 epochs. You see this, and it provides these metrics, what percentage is run, and so on. So all of that is happening, and we get this fancy chart as we begin to run the number of, this is the loss, the blue value is the training loss, red is the, or whatever this color orange is the validation loss, right? So what we have done is starting with a very basic, before this we just had fit and it was hard coded. We could do just a certain number of things in fit. Now with a few quick steps and with the concept of callbacks introduced into it and a few other bells and whistles, we've been able to build a framework that where every single line can be modified and some nice charts and plots of our training can be displayed so we know how training is progressing with our network. So this is where he explains why he switched from using context manager. So here's the problem, that it doesn't somehow raise an exception before the yield function, details that aren't important for you to know, but we switch to using a decorator-based callback. Now, a decorator-based callback is done first with the class called with CBS. Now, again, it's important to understand what decorators are and also what a decorator factory is, because this is a decorator factory. By that, what I mean is the with callbacks actually, when it's called, returns a decorator, and the decorator then decorates the function that's passed into it. Okay, so again, I think Mike even responded. I provided the Luciana Romalo's class, I think from 2019 on decorators and parameterized decorators. I would highly encourage you, if you're not familiar with the concept, and to kind of go through the 2.5 3-hour lectures. You can ignore the descriptor part of it, but decorator part of it, you should definitely go through to understand what this code is doing. The one thing that I would point out to you is and it took me a little bit of time to get this, is the fact that the O object passed into the function here is an instance of learner. So when that's O.callback, it's actually learner.callback, right? So we see how the with callbacks. So this is a parameterized decorator factory, which means that depending on the parameter that is passed to it, it will generate a decorator with the particular parameter, and the parameter in a sense will be things like before fit, before epoch, before batch, after fit, after epoch, after batch, and so on. So what this with callbacks function does is it stores away the name, like this, you could say fit or epoch or batch, because the before and after are hard coded here. And then when you pass it a function, that is whatever your callback is, it will call not this function, but it will call and return the function which is coded here. Assume that there is no exception, and it will do the following thing. It will call the callback, which would be before whatever you passed in. So if it's, for example, fit, then it will say learn.callback before fit, and call the function that you passed into it, pass it the learner, and pass it the arguments, star args and star keyword args, then call learn.callback after whatever you passed to it. So if it's fit, it's after fit. And if you have not raised an exception, the other thing which it does, this callback does, which we didn't do previously, is it also calls callback and says clean up after fit, or clean up fit, sorry. So there is code that is executed before fit, which will be described in the callback. There'll be code executed after fit, and then there'll be code executed called cleanup fit, because if you want to reset some things after you're done. And this happens for each of fit, epoch, and batch, and can also, not through this mechanism, because we'll not use with callback, but obviously we'll still use callback for the 5 things which we've seen before: predict, loss, opt, backward, and so on and so forth. So those are the changes that he makes. I would encourage you again to go through the code. This code, I'll explain it very quickly, but if there is questions and you're not clear about what is happening, feel free to ping and or ask the question in Slack. So this is the final version of the learner that we'll be using as we move through the rest of the course. So here we have a learner, do the same thing, store the callbacks in the callbacks, store the attribute, and here's where we begin to modify the stuff. The first thing, as always, is we go to fit. The callbacks are stored away in here. The one change that you will see if you compare it to prior versions of Learner, he's allowing you to pass in a new set of callbacks directly to the fit function. Okay, and that is a change if you go back. And also, he's allowing you to pass or a new learning rate. So if you don't, it will use the learning rate from here. But if you want for a particular fit to change the learning rate and for a particular fit to change the callbacks, you can do that because now you have the ability to pass in a new learning rate and callbacks to the fit. Store away the callbacks in the callbacks, right? And then
what
again,
is fc.l?
That's what I talked about earlier, Mayank, that L is the L class, which is similar to the list. You can go to, I'll provide you this. There are some pointers for the L class in Passport.
Okay.
It's essentially a list, but it's an enhanced list. He throws in some of the NumPy capabilities of indexing to a list. It also shows the number of elements to you when you print it out. It shows the early elements and the last elements. So it has a lot of convenience function built in that list traditional Python list doesn't have. So that's what it is. fc.l is just Passport's L class. Right, and then store the attribute, then come to fit. He adds the callbacks. As I said, he has added this ability to provide callbacks. And we obviously need to add to the callback for CD in CBS, self.cbs.append the callback. Then try number of epochs. There's nothing new. If LR is none, then LR is self.lr. That means if you haven't provided any LR to the fit function, make it come from the learner class. In an opt, it's just the model parameters and LR. So he allows you to change the LR, which you didn't have in the, if you go back and look at the previous version of learner. And then he calls self._fit with train and valid. Okay. So now from here, we'll go to _fit. So what is _fit? Now, _fit is the function that's going to be decorated with the with CBS factory decorator passing in fit. So when we do this, what we need to understand is that when we pass in _fit with CBS fit, then we are actually passing in what we will get out of this with CBS fit is this function _f, where these lines of code will be executed, okay? Not the actual this function, right? But bottom line, what it means is first we'll go in and execute learner.callback before before, and then it'll be the method name, which in this case is underscore, so it'll be before _fit. Then it'll call what we have said, which would be the function that we have passed in, which in our case is the _fit function, which means we'll execute this for self.epoch and self.epochs. If train, then we'll say self.oneepoch is and pass in true. So it will go execute the one epoch, and one epoch, what is one epoch? One epoch is here. So one epoch, and we can take the value of training. We just put the model in whatever mode it says to put it in, get the appropriate loader, and then call self._one epoch. The _one epoch is going to be decorated again with CBS epoch. It'll again go in there and it will execute the, in this case, it's passed in with epoch. That means we'll go execute before epoch and then execute self.epoch. When I say execute before epoch, I mean execute the callback code that's there when we say, remember, this is execute the learner's callback before epoch, then call this function. So then it will come back, execute this line of code, and once that's done, right, one epoch, it will execute self._1 batch. Self._1 batch is again decorated with CBS batch, goes in, executes that, but within the batch is where there will be these 5 callbacks as well: after predict, after loss, after backward, after step. Right? So we have seen this before, and we'll do all these things. And eventually, after we are done with all the fit, the epoch and the batch, all of them decorated, because you want to make sure that you execute the before and after. And there is also this finally. So in try except loops, finally always execute, regardless of whether you execute the try loop or the exception portion of the code. Finally, it's always executed. So the control flow is, if you don't get an exception, you execute that. If you get an exception, you execute this. Regardless of whether you get an exception or not, you execute finally before you exit. So it will execute that part and get out here. And then again, because this is in a try except loop, it will execute this, which means it removes all the callbacks from the callback. Right? Just to keep things clean, it kind of cleans up after itself. The rest of the code is things we have seen already. This is fairly involved, but at the same time, if you've been following the build-up that he has done step by step and explained, okay, I'm now injecting the concept of callback, but I'm now doing it with decorators. And if you understand the concept of decorators clearly enough, then you should be able to clearly understand what's going on and how he provides the immense amount of flexibility of modifying almost, or providing the ability to us to modify almost every line of code in our training loop without changing the framework.
Yeah, there's one comment here. I suppose if he wants to avoid the use of callback, he could have done so with the use of decorators only. I mean, in this _1 batch method, the callbacks of self.callback, after predict, self.callback, after loss, after backwards, after step, and they could have been avoided if we use @ with CBS methods after each one of them. So there's one thought here.
Yeah, except I don't know. I mean, usually, yes, down the road, we find out why he chose to do certain things in a particular way. So I would reserve judgment as to whether that's a better way or the way he has done it. Because usually he has some pretty good reasons that we discover. Like, for example, as we go down the course, as we go down the lessons, as we go further in the lessons, we figure out, oh, this is the reason he did it that way.
Yes, that's true.
So, for example, the number of inputs is not something that he initially included. He initially thought context managers would be a good way to do it. He gave up on it. So I think, yes, it could be, but I'm sure there are good reasons why he does it the way he does it. Okay, so now we just want to make sure that this new learner with all the decorator functions utilizing the callbacks and stuff works the same way. So we just provide the model, use the same callback, the train callback, the divide callback, the metrics, and the progress callback, and make sure that all of that works as before. Right, so nothing new, just want to make sure everything works as before. Let's see whether I have, yeah, so this is something I already explained, but you can read the comment that basically the learn.fit also has a callback parameter and an LR weight. So these are just added. Again, these were not, if you just looked at the video, he covers only a portion up to, the code is different from what he covers in the video. And the reason for that is he updates, and this comment, right, updated versions. And then I added some of the comments that he makes in a subsequent lesson that he talks about how he has modified. So that's kind of, and these type of things help me when I go back and figure out and I'm playing with the things later down the road, and I want to understand why things work the way they do. And again, he says certain things. For example, why don't we need to say torch.nograd, but instead we just call torch.nograd self.oneepoch false. So for example, what he's talking about there is here. So this line of code, he's asking, why don't we have to say with torch.nograd? Instead, we just say torch.nograd and we call it, and then we pass in a self.oneepoch false. Can everybody answer that? And if you look into it, at least my answer is actually, if you look into PyTorch code, you'll figure out that torch.nograd is a context manager that's also a decorator. So when you do torch.nograd and call it, it's a parameterized decorator. So it says decorate the thing that's coming after. So you don't need to do with torch.nograd because it's a context manager that's also a decorator. So you can just call it as a decorator and then pass in the self.oneepoch and the false. So this function returned by that is decorated by torch.nograd because torch.nograd, you can use it as a context manager when you say with torch.nograd. But torch.nograd in PyTorch is also a decorator. So and actually, therefore, you can use it as a decorator. That's the reason this line of code works. It's different from what we've done before. So these little things when you watch and he kind of throws in, it's good to pay attention and kind of look into it and figure out why, because that helps you teach more about what's happening in the code. Okay, so we've seen this. Now, we've seen one of the ways, in fact, to your point, although you were talking about using it as decorators, but there is a different way to do the get predict loss and things like that, instead of providing them in the callbacks as callbacks. Because remember, two things are working together in our learner. One is the learner and the control loop that it goes through. The other is the callbacks, which provide us the ability to execute some functions. But now we have provided these 5 things, right? Predict, loss, and things like that. But those are one way to execute them is to execute them as callbacks. The other way to execute them is to execute them as a learner subclass. So instead of using the train callback and specifying what to do when we call those attributes of the learner, we could subclass the learner class and add those methods. That's another way we can do this, right? So that's something he explains in the next several cells. So what we want to do is subclass the learner class to a train learner and define the 5 methods. So in predict, we just say self.predict, that in the learner's prediction is what we want to do with it, self.loss. So these things are what it does in the code is fairly self-explanatory. The fact is that we have just inherited from the learner class, created a train learner, and defined the 5 methods that we wanted to define that weren't defined in our base learner, right?
Yes.
Go ahead.
Yeah, I had a query regarding the first line here. Suppose the def predict in which in the end he says self.model self.batch 0. So it's the 0th index that will be executed here.
In this case,
what about the first, second, third? For the predict function.
He is, I think, just using it to do it in this case for a particular example. But you could generalize this. There's no reason that it has to be this way.
Okay.
Right? He's just, in this case, just illustrating to you what can be done. But there's no reason to necessarily do it or limit it to self.batch 0.
Yeah.
It could just be self.batch.
Yeah, that's what I thought, because in this way it will be hard coded. And
Yeah. And he's just saying you can do it this way. I don't know that you will, or there's no reason to limit it to just 0 and 1 index.
Yes.
Okay. Now, as we go through the next several lectures, we will really understand the concept of what momentum is and how the concept of momentum is used in order to accelerate our learning. Okay, and in order to get us to find the best solution or the most generalizable solution that we can get through our training process. In my opinion, unfortunately, he introduces kind of the concept of momentum in the form of what is the concept of momentum. The momentum just says use a weighted average of the values that you've accumulated so far in order to modify a value. So if you've been collecting a certain number, if you've been collecting certain gradients, then you say, how much of the collected value of gradients should I use to update my gradient, and how much of the current calculation from the current batch should I use to calculate or influence my gradient. So that's the concept of momentum. That is, how much should I weigh the average of everything that I've calculated so far, and how much should I weigh the value that I get from the current batch. Let's say we have executed 10 batches. Then how much of the 10th batch should I factor in to my gradient, and how much of the 9 batches that I've averaged and calculated previously, and I've calculated the average of those 9 batches. What fraction or what weight should I apply to those 9 versus what weight should I apply to the current batch? That is the concept of momentum. Now, he just uses it in kind of not the way that you would use in the optimizer, which we will see later. But at this point, what I think he's illustrating is, oh, you can take the train learner and subclass that and build a momentum learner. You pass in the value by which you want to average your stored values and store it away in momentum. And then you initialize all the things that you would pass to the base class again. And then when you want to define, now remember that 0 grad is defined here, right? So when you do the 0 grad with torch.nograd for all of your models, you just modify the grad by multiplying it by the momentum. So this is not how traditional momentum works in the optimizer and stuff, but he's just saying, oh, let's just play with it. Let me illustrate to you that we can build, just like we built a train learner, we can build a momentum learner where we can provide in a momentum value, and that in turn will go back and modify one of our methods that we have defined in the train learner. And by the way, Mayank, I think because he's using it in the concept of momentum learner, he's just using it as probably doing this 0 and 1 business here, which he doesn't have to do for the generic case. Right, so do that, and then you just use the same callback, but instead of using the traditional learner, we build the momentum learner, right? And we see what happens to the fit function compared to before. But the more interesting, I think, because the momentum learner is not all that, it's just something that he suddenly thought of and wanted to play with. But the much more important and interesting callback to build that we should discuss more is the LR finder callback. So LR Finder or LR Find is something that the FastAI library first introduced. Essentially, it's based on a bunch of papers. You can read the papers. There's a lot of detail and it's very interesting work. Bottom line, what it says is, if we train at a high learning rate, we get not only faster convergence, but we also, it turns out, get neural networks which are able to find better, more stable losses in the contour of the loss function. And at the same time, they are, because of this, they're also much more generalizable. So high learning rate has multiple advantages. So if you want to train a neural network, it's good to know what approximately is the highest training rate that you could potentially train the network with. So how do you find that learning rate that gives you what do you want to start the learning rate at, right? So the way you do that is you start with some learning rate and you start training the network with some learning rate, and you continue to increase the learning rate by a certain value. So you first start with some learning rate, find out the loss, increase the learning rate by some multiplier, train the network again. If the network loss goes down, increase the learning rate even more, train it again. If the loss continues to go down, increase the learning rate. At some point, when you increase the learning rate too high, the loss will begin to go back up. Now, in order to understand that, you should probably look at, if you don't get the loss function contours and things like that I'm talking about, I would highly encourage you to go offline and look at many posts such as this one. I'll post a link to this, but there are a million posts which show better diagrams and stuff. But the bottom line is you're trying to find, through gradient descent, kind of the bottom of this graph. And it's actually much more complicated because of various issues that get in the way. But what we are trying to do through the optimizer is find this spot which gives us the lowest location, if you will, in this contour, right? And when we use too high a learning rate, we may miss that point and go back up in the loss and therefore increase the loss. That's the point at which we back off and we say, oh, now the loss has begun to increase, not decrease, as we increase the learning rate. So that will cause our loop to stop. So what we do in the LR Finder callback is, as I said, the concept is we can, start with some learning rate, increase it by multiplying it by something after we have calculated the loss, recalculate the loss. If it continues to go down, we continue to increase the learning rate. When it increases, and by a certain amount, we choose to stop. So store the attributes away. We have a multiplier that we want to apply to the learning rate. We store the learning rates and the losses before the fit. And we make the minimum to be positive infinity so that any value we calculate, we can put it in the minimum first. And after that, first we check we are doing this in training, because obviously we are interested in only increasing the learning rate and finding the learning rate while we are training. If you're not in training, we just say, forget, cancel epoch exception. Then we store the learning rates in the LRs, right? And this is a detail that we need to know about, that the learning rate for our layers is actually available in the optimizer under the param groups of our optimizer. So in this case, the learn.opt.param group zeros, and then the learning rate is the learning rate that we want to grab onto, which will be our base learning rate. Keep track of the loss. So we calculate the loss, and we've already defined the 2 CPU, move the loss to that, and then append it to the losses. And here's where we check and adjust our learning rate. If the loss is less than self, then we put it in there because it will be infinity first. So whatever value we calculate will first go in will go in loss, self.min. And then if the loss is 3 times greater than the minimum loss. So we continue to increase our learning rate until we see that we have increased, until we observe that the loss has increased by 3x compared to the minimum we have stored so far. So if the loss increases by 3x from our minimum, we say stop. And we don't grow our learning rate anymore. That's why we raise cancel fit exception. And then for every case where we do not stop, that means if loss is less than cell.min is lost, and then we grab the learn.parameter groups and we make the learning rate the updated learning rate, which means we increase the learning rate by 30% in each step or each epoch. Is that clear as to what we are trying to do here? Okay, and then now we just define an instance of LR-find and we execute using our infrastructure. And we just execute one loop. So you can see here that this is the learning rate, and we continue to increase the learning rate all the way from -4 to -3 to -2 to -1, and then when we kind of somewhat come about to about, I don't know, 0.1 or close to 1. No, this is 0.1, so larger than that. As we get closer, then at some point the loss just shoots up. So typically what he'll say is we should pick somewhere in the steepest part of our curve as the learning rate. So we will probably pick something like 0.1. We could even pick 0.2 as our learning rate. That will be an excellent learning rate to start learning. Right? Now that we have coded the LR Finder callback ourselves, we can kind of use PyTorch's exponential learning rate finder. Certain things which he points out that the documentation of exponential learning rate is actually wrong. The reason for it is it says, there are two things. There's a gamma given, and then there are the max multiplier given. And gamma is the multiplicative factor of LR decay, it says. But obviously, as he points out, if gamma is greater than 1, then actually it's not LR decay, but it's LR increase. So just be aware as you go and look at the exponential learning rate that there is a mistake in the documentation. The PyTorch increase in increase in the learning rate and things are done through schedulers. So the other mistake in the documentation he points out is the PyTorch schedulers have a step method, and this decay, I've had it in quotes here because it's not always a decay, as you just saw, it could be increased, happens every time you call the step, not every epoch as the document claims. So every step of the scheduler, the multiplication or the gamma increase or the gamma decay happens. Okay? And so we recode the LR Finder callback using the scheduler of Python and the scheduler of PyTorch. So the difference between how we have coded it and here is we now use a scheduler and we call it a set.schedule, and that's an exponential learning rate, and then we pass in the optimizer and the gamma value into the scheduler. The rest of it should look very similar. There's nothing else that I think, these things are very similar. The only thing here is he kind of adds code to if loss has any values, any man values, then raise exceptions. And finally, instead of saying, oh, for every G in our parameter group, blah blah blah, all that is hidden behind the scheduler. Scheduler takes care of taking all of those things, takes care of figuring out all those things. So instead of doing this piece of code that we had, we just step the scheduler. And this is where it's important to know that whenever we step the scheduler is when we increase or multiply the learning rate, not after every epoch, because remember, this is happening after every batch. And then we do this cleanup fit because what we're doing in cleanup fit is we plot before we exit. So that is a utilization of the PyTorch scheduler to do our LR find, and we finish that. Now, here's another interesting thing he does, and this is explained, in fact, not in the particular lecture about the learner, but in lecture 18. But because it's a lot simpler for us to just say, build a learner object, and let's just call LR find of the learner object. And it would be great if this LR find becomes a method of the learner class, because then we could just say, here's a learner model, blah, 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 what we supply to it, and then call an LR find method. But there is no LR find method in the learner class. Well, here comes the patch functionality of FastCode, where if you look at the FastCode patch functionality, and again, you can go, I'll provide the link directly to the patch functionality in FastCode. What it does is it takes any function that you provide, and if you provide the base class to which you want to attach the function as a method, you just define an FC patch decorator, fc.patch, and you define the LR find and you pass in the values to it. And within it, you obviously call the self.fit. But what this patch decorator does is it sticks LR find as a method into our learner class. So it binds the LR find function to the learner class. And it's just a version of monkey patching, best I can tell. Right. So now, and as I said, that's not there in learner, but it is there in this notebook. So it's covered though of what is happening here in lecture 18. I wanted to all be in the same place as we're going through the notebook. It's just a shorter way of using the LR finder callback. So now what we can do is you can just say momentum learner, get model, DLS, F cross interface, callbacks. This whole thing up to here is just our learner. And then you can just call LR find method on it. And the LR find method takes this learner and these values, gamma, max mult, start learning rate, and epoch. And obviously start learning rate is where you start it off with, and then you keep multiplying by gamma. But the max multiplier, I guess the scheduler for PyTorch is, don't go above 3 or max multiplication value, and self.fit, and you do that. So now you run momentum. Oops, I did not. Okay. So that is our learner class, the ability to kind of really speak just about every line of code in our learner to customize. And this learner class will be heavily used throughout the rest of the course. And I think it is a really excellent, probably the best, most customizable training loop that I've ever seen. Now, often in Kaggle and stuff, you don't see people use it at all. And that's because in Kaggle or any of these things, if you're doing one particular thing, then it may not be the best framework because it has some overhead. But if you want to experiment with many, not just networks, but many data points, want to quickly try a variety of different options, tweak variety of parameters, I think there's nothing that exceeds the ability to kind of manipulate what you want to do as part of the training group. Now, all this, we have spent a couple of hours just understanding the learner. The next step of the same lecture is understanding how do we utilize or how can we understand more about the activations that are actually taking place in the neural network. So far, we have just looked at modifying the loop of training that we put the model to. But what are the parameters of the model? How do they change as we go through training? How do the parameters of the layers that are deeper into a network or layers at the beginning, do they have a relationship? Are they training well? What does training well mean when we train networks? So those are all things which we would, again, want to build the flexibility to know and understand when we are studying neural networks. And that is done as the part of this lecture. Unfortunately, given the time, we'll probably cover that in the lecture next week, which would be all about hooks and hooking, forward hooks and backward hooks in PyTorch, the concept of hooks, and with everything else, we'll code it ourselves, and then we'll switch to the PyTorch hooks in order to understand how the parameters of our model change. And are we, remember again, the motivating factor for this problem was we were not making much progress with our MNIST autoencoder. And we want to kind of get to the point with the autoencoder where we are providing results that are or classifying MNIST not only very quickly, but very efficiently, such that our results are comparable to the best state-of-the-art results that people are posting. So we can only do that if we provide the ability to customize our training loop. Secondly, understand how our neural network parameters are changing, or how best to train our neural network so that we can train it fast, and we can train it to give good performance, and we can train it to be highly generalizable. So that's the second part. We'll look at that in the next lecture or next week. Any questions left? If not, thanks for joining, everybody. See you all next week.
Thank you.